Hello everyone, let us see now next point of this fifth chapter. This is the last point, last method, Yoon's method. Let dy by dx is equal to f of xy be the given differential equation which we want to solve with the initial conditions x0 and y0. The formulas for first iteration is for I is equal to 0. This will be our first iteration or first step for the first step. In the example itself, they can ask for many steps. For first step, second step, depend on the value of h. Okay. Now this formulas you can generalize for n number of steps. The first formula for first step, that is for I is equal to 0, that is first iteration. It is the first iteration. Y I plus 1 not. This is a general formula. First iteration will be for I is equal to 0 is yi plus f of x I into h. Okay, this is the Euler's method first formula. In this Yoon's method, they used first step as the formula for Euler's method. Now go on increasing these iterations. Y first, this is 1. It is not dash, it is first. It is 0, it is 1, it is 2. Okay, I plus 1 is equal to yi, this first term as it is, plus the addition of two functions f of x I yi, this as it is, plus f of x I plus 1, next x comma y I plus 1. Y I plus 1 not is this value. Whatever this calculation is, we have to put this for value here in this function. We are using earlier value here. Whole divided by 2, it is average of these two into the ch as it is. Okay, in this formula the function is only, this is the only difference in this step, otherwise rest two things are same. Okay, now next second iteration of this first iteration, this is a different method. It is like Euler's modified method only. This term as it is, this ch as it is, and in this term everything is same except this function, except this term. Y plus 1 not is the earlier value. Here we have to just replace in this step y plus 1 not by this value, earlier value, y plus 1 1. Okay, in the calculator we have to just delete this number by this earlier value and just calculate the value, and so on. Now next y 3 I plus 1 will be everything will be same except this value should be yi plus 1 2, this one, this term in the next iteration. Okay, and so on. You have to do this step or do this formulas calculations until we get two consecutive formulae same. Two consecutive formula values are must be same. Okay, this is our first iteration. If we are going to, if for next iteration, that just replace I is equal to 1. Everywhere just replace I is equal to 1 and do the same procedure for next iteration. Okay, now let us see the example. Now solve dy by dx is equal to y x square minus 1.2 into y. This is the differential equation. That means f of x y becomes this function. Using Yoon's method is given already in the example. Given y naught is equal to 1, that means x naught value is 0, y naught value is 1. As usual, this is a initial condition. Over the interval 0 1, that means this is over the interval, means these are the values for x. Okay, solving the equation means we have to find values of y. That's why formula contains LHS said y. Now taking h is equal to, they are already given h is equal to 0.5. That means 0 to 1 is our interval, and we have to take a step of 0.5 means half, means this is the example of two steps. Okay, this is step number 1, and one more we have to do for step number 2 for I is equal to 1 in this particular example. It depends on the value of h. Okay, that means 0 to 1, these are the x values. We have to go up to two steps, taking h is equal to 0.5. This is x naught value, which is already given also. Y naught, x naught is 0, this is bracket value, y naught is 1, this is already given. From x naught we have to reach 1 through the step 0.5, means this is a two step example. This is value x naught 0.5, this is first step, that is x1, and last one value adding 0.5 to 0.5 we get 1, next x2, and corresponding to x naught we have y naught. Now we have to find out for first x1 corresponding y1, that is first iteration, and for x2 corresponding y2 for second iteration, means second step. Okay, this is the two step example. Okay, one by one let us start the solution. Let f of xy is equal to this function. It is already given in the theory, that is whatever dy by dx is equal to on RHS side, that will be our function. This is function. Write this as it is. Now take h is equal to 0.5. If it is not given, you can take as per our convenience. H is equal to 0.5, x naught is given 0, y naught is 1. This is the given value. Now take a first iteration, that is first step, for I is equal to 0. Put I is equal to 0 everywhere in the example or in the formula, and we have to calculate. X1 for first iteration is for first step is for x1. Second step is for x2. Okay. For x1 we have to find out value of y. That means y1 here. Okay, this is the first step. Now start putting the value of I is equal to 0 here in the first step. We get y1. This is I is equal to 0. We get y1 0. Y naught, I is equal to 0 here. Y naught plus f of x naught y naught into h. Okay. Now put the value. Y naught is given 1. F of x naught y naught means we have to put in this function x value as x naught, y value as y naught. X naught is 0. That means in this function we have to put x is equal to 0 and y is equal to 1. Okay, whatever the answer. Into this h value is 0.5. Calculate on calculator, we get 0.605 is our first approximation of this first iteration. Okay, now second, this one, y I value becomes 0 here, we get y1 1. Y naught plus f of x naught y naught plus f of x1 and y1 naught divided by 2 into this h. Okay, now put the values. Y naught is 1, it is given. F of x naught y naught is same as earlier. In this step we have calculated as this. Put x value is 0 and y value is 1 in this function, we get this function value, plus f of x1 y1 means we have to put in this function x value as x1 is 0.5 and y1 1 is this y1 naught, it is not there. Y1 naught is this value 0.605 in the given function, we get this value, this function, whole divided by this 2 as it is into this 0.5 as it is. Now make the calculation on calculator. Answer is 0.555563 is the first iteration, that is first approximation of the first iteration. Now second, y, put the value I is equal to 0 here, we get y12. What is the difference in these two function formulae? Just replace here y1 not to y, this is 1. y11 means this earlier value. Okay, now like this step, put the value of this is as it is here. In this step just y11, this 0.605 can be replaced by only 0.5563 here in this function only. That is the only difference. Into this h, rest of the terms as it is. Put the values, we get the answer 0.56787. Okay, now comparing these two, up to what which step we have to do that? Until we get two consecutive y values should be same. This is 0.5563, this is 0.56787, means we have to do one more or two more approximations. Now put next y13 here, third approximation of this first iteration. Put everywhere y I is equal to 0, we get this formula. In this formula, what we have to replace? What is the difference between these two? Just replace y11 by y12. That means this value here, and put all this function as it is here in this step. We get 0.56512. Okay, now these two are equal. 0.567 and 565 means both are approximately equal. And if you go to next iteration, you will get the exactly same as this. That's why we can stop here, and the first iteration, that means first value y1 of this 0.5, answer is y1, that is y of 0.5. Answer is earlier, the latest value of y, that is 0.56512. Okay, this is the first iteration using this Yoon's method. Okay, now this particular example is of second step, that's why we are now going to solve it by second step. Okay, now second step means second iteration for x2. X2 is this x2 for 1. Okay, why we have to find y2. Y2 of bracket value is 1, x2. We have to find this. This is our second iteration. Now in this second iteration, what we have to do? Just putting I value is equal to 1 everywhere. Okay, now in this particular iteration, we need x1 and y1. In earlier first iteration, this one, we need x0 and y0, which is already given in the example. Now in this next iteration, we need x1 and y1. And what is x1 and y1? X1 is in earlier steps answers. X1 is 0.5 and y1 is our latest answer in the first iteration, that is 0.56512. Now we are going to use these answers in this particular formula. Okay, x2 is 1. X2, we also need x2. Now let us start with the second iteration. Y2, put value I is equal to 1 in this formula. For second iteration, for I is equal to 1 everywhere, we get y0 as it is 1 plus 1 is 2, and y1 plus f of x1 y1 into h. Put the value y1 is 0.56512 plus f of x1 y1 in the function, this function, we replace x by x1, y by y1. Answer is 0 y, this is 0.56512 y1 into x, that is x1, that is 0.5 square, minus 1.2 into this y1 is this. Okay, put the function in the function value, this you have to just replace this x1 y1 as it is. Okay, into 0.5, this h throughout the example will remain same, 0.5. Now calculate on the calculator, we get first zeroth approximation of this second iteration is 0.2967. Okay, now next y1 plus 1 2, y2 1. Put the value I is equal to 1 everywhere, we get this formula. Okay, now in this formula, y1 as it is, f of x1 y1 is this step as it is, plus f of x2 y2 means in this function replace x by x2, x2 is 1, and y by y2, y2 not is this earlier value, we get this step. Bracket complete into h as it is 0.5. Now calculate on the calculator, we get 0.2670. This is first second approximation, this second iteration. Now next y22, put I, this one, this value, this formula, I value is 1, 1 plus 1 2, 2 2 everywhere, we get this formula. Again in this formula and this formula, just only one difference is there, y2 not instead of here y2 1, that means this value we have to just replace everywhere here, and into h this y1 as it is. Calculate on calculator, we get y2 2, answer is 0.2699, and this value almost same, 0.267. 2699 is almost 267. We don't need to go for further iteration. That's why final answer will be y2. 2 is our second approximation, that is y2. We have to find y2, that means y of 1. In the final answer you can delete this suffix. Okay, this is our second step answer, and this is our first step answer. Okay, this particular example is of 2 steps. Okay, now these are some homeworks for you. Solve dy by dx is equal to 2x minus y naught is equal to 0.9. This is x naught is 0, y naught is 0.9. Find y at x is equal to 0.2 and 0.4. Okay, in this particular example interval is not given, but h is given already. See, y x naught is 0. Okay, that means we have to start with 0, and we have to find out y, value of y at x is equal to 0.2 and 0.4. That means what is value of h then here? 0.2. Difference between these two are same, 0.2. Okay, that means this is also an example of 2-step. This is a 2-step example as earlier, and function is only different. These are the answers. Okay, now this is also homework for you. Solve dy by dx is equal to y minus x upon y plus x. Y naught is equal to 0 means this is x naught. X naught is 0, and we have to find y of 0.1. This bracket value is x value. 0.1 we have to find out, that is y1. This is only first step example. Take h is equal to, in this example we are not asked for how much we can take h or how many steps are there. That's why we can take any number of steps. That's why conveniently take only one step. This is one step example. That's why for this only one step for h is given. H is nothing but difference between these two. This is x1. For this particular, this is y naught is given, and this particular for y1 we have to find. Okay, take h is equal to 0.1. Answer for this question is this, 9828. Okay, this is the end of our 5th chapter. Now let us see now next chapter. This is our first chapter, the error analysis. Okay, let us see. This is a very theoretical chapter. Introduction. Although the numerical methods, techniques, we have already seen so many numerical methods: Euler's modified, Euler's method, Runge-Kutta method, Yoon's method. Okay, in these particular methods, we face some errors. And what kind of errors we are going to face? We are at that particular in that particular numerical method examples, we are using approximate values, okay, in each iterations. That's why those errors occurs. What type of errors are those? We are going to see in this particular chapter. Okay, let us start with the introduction. Although the numerical method techniques gives the solution close to the exact analytical solution. What is analytical solution? Whatever the theoretical solution of the particular differential equation is the analytical solution. That is a exact solution, and we are by numerical method techniques or numerical methods, we are solving those examples and getting approximate values. Okay, there is a error because of that approximation, and let us see some terminologies. This is in particular question type. Explain accuracy and precision with illustration or with the sketch, illustration or sketch. Okay. The error associated with both the calculations and measurements can be characterized regarding to their accuracy and precision. Okay. Now, what do you mean by accuracy and what do you mean by precision or preciseness? Let us see. We already know these two words, but what is the exact meaning of those words? Let us see. before going to this error analysis. Okay, accuracy, it means how closely the individual computed or measure values agree with each other. For example, consider the example of target practice. Okay, the bullet holes on each of the target can be considered as the prediction of the numerical techniques, and the bullseye mean the our target, okay, as a truth. Okay, now inaccuracy means it is the systematic deviation from the truth. Accuracy and inaccuracy, hitting the target is nothing but the accurate, how much degrees we want, how much closely we are supposed to hit the target. The bullseye means center of the target, and inaccuracy means the deviation of our target, how much far from our bullseye, hitting our bullseye is the inaccuracy. Okay, now impreciseness or uncertainty, it means the magnitude of scatter, how much scatter diagram we know, means how much density is there of hitting the target. That means the scatterness of the points, and more the scatter points means less the precision. Okay, or uncertainty. For example, these are suppose the four targets. Okay, this is the bullseye, means center of the target, and these are the hitting of the bullets. Okay, now in this particular see this the in this two, how much accurate the hitting of the target is nothing but the accuracy, and we have to make the precision also. Okay, now in this particular first hitting target diagram, uh, but the middle one is our bull eye. Okay, we have to fit this bull eye is our target. Now in this particular example, in this particular target, the points are scattered around the this target, away from this target. That's why these are inaccurate. This is also inaccurate, but in these two particular targets, the points are scattered equally around the target, means they are close to this bullseye. That's why these are accurate, but these are not accurate. Okay, these are equally spaced, that's why they are accurate. These are not equally spaced, these are away, the few points are away from each other, away from the bullseye. But in this particular two examples, targets, our points are equally spaced to the to our bullseye. That's why these are accurate, these are not accurate. And preciseness and impreciseness, see, in this particular do these two examples, points are less scattered, less scattered. Okay, these points are very close to the all points are close to the our bullseye. In this example also, all points are equally close to the bullseye, but in these two examples, points are not close to our hitting the target, to our target. That's why these are precise, actually precise hitting the target, and these are the imprecise hitting the target, our bullseye. This is the difference between accuracy and precision. Okay, how much points are scattered around our target, it depends on that. Okay, now let us start with exact calculations of our um, chapter, that is error analysis. Let us start with the error definition. Numerical error analysis arise from the use of the approximation to represent exact mathematical operations and quantities. Okay, now true values is equal to approximate value plus error. Whatever true value means analytical solution of our particular differential equation, and approximate value means whatever the answer we are getting from numerical methods, and to add that particular error we get the exact true value. This is the simple logical statement. From this statement we get error is equal to, they take true value on approximate value on that side, we get true value minus approximate value, means analytical solution मधून जी व्हॅल्यू आपल्याला मिळते एक्झॅक्ट सोल्युशन थेरॉटिकल सोल्युशन त्याच्यामधून ॲप्रॉक्सिमेट व्हॅल्यू सेम एक्झाम्पल solving by numerical method, whatever answer we are getting, that is approximate value. These are two different values, slightly different values, and difference between these two values nothing but the error. Okay, that is particular numerical value. Let us see the next types of error. There are number of types of error. Let us start with the first. Inherent error. Inherent error means heritage. We are using inheritance or inheritance error means in this word itself the error which present in the problem itself before it is going to solve, okay, are called inherent errors. It can be minimized by using the better data. Suppose in the example itself there is some error and we are carrying those values, initial values to solve the particular example, then we get obviously we get the error, and that type of particular errors are nothing but the inherent errors which are actually present itself in the problem itself. Number 2, rounding errors. Rounding itself is the definition for rounding errors. These words contains rounding means in particular presenting the number in the decimal places, we round off some numbers. We always do this step while calculating the approximations or iterations. Okay, that type of error is nothing but rounding error. The error which arises due to rounding of the numbers at various stages of the solution or steps in the computation or calculation. For example, value of pi, value of e, and value of such different mathematical numbers are considered by neglecting the terms by rounding them. For example, suppose 19 upon 7, exact answer is 2.714285. But what we take in particular our calculation, only 4 digit. We do these things, okay. 19 by 7 is 2.714, and by using fifth number we round off the fourth digit, that is 7143, and by neglecting the numbers we get the error. That type of error is nothing but a rounding of error. Okay, now next, truncation error, and the point in our syllabus is also Taylor series using truncation error. The error which arises due to cutting off the lengthy series at a particular point given in the example. Let us for example suppose the earlier example, 19 upon 7 we take this, but we take 19 upon 7 as, if we take 19 upon 7 as 2.7142, and cutting off the or chopping or cutting off the numbers from 85 or further, we have that truncation error. The difference between truncation and a rounding of error is this: for rounding off we round the figure using fifth decimal point, we round or increase or decrease the increase or keep as it is the fourth digit. This is called rounding off. And truncation means we are not rounding off the number, we are just deleting or chopping or cutting the numbers from the fourth digit, okay, and take the 4 digit as it is. We are not going to round off. That means the truncation error. For example, suppose e raised to x, this is a series, this is a Taylor series for e raised to x, 1 plus x square by 2 factorial plus x square by 3 factorial plus x raised to 4 by 4 factorial plus x raised to 5 and so on. This is the infinite series, okay. But at a particular point, if you want to calculate e raised to x, we take the only first non-zero 3 terms or 4 term. Suppose this is e raised to x, in particular calculation we take only up to this third or fourth step. Suppose this is x1 and this is suppose x2, and this is obviously the bigger one, Infinite series obviously the bigger one than this. That's why difference between these two is nothing but the truncation error. Actual value minus approximate value, same definition. And in this particular example we are using series of numbers. That's why it is called the truncation error. Now third example of truncation error. Suppose speed of light in vacuum is 299792458 meter per second. Okay, this is expressed as, we know this can be expressed as, we mug up this number as 2.99, take a decimal point, shift it to left to 8 decimal places, that is 2.99792458 into 10 raised to obviously 8 digits are there, but meter per second, but truncated to 2 decimal places, we know this particular standard number of speed of light 2.99 into 10 raised to 8, or sometimes we consider 3 into 10 raised to 8 meter per second. Okay, this is called truncation error in the particular series. Now truncation error can be calculated actual value minus truncated value. Actual value is this, okay, minus truncated value or chopping value or cutting value is this. The difference between these two is 0.00792458. Okay, shift decimal place to 3 points towards right, we get 7.92458 into 10 raised to minus 3 is called truncation error. Okay, next, absolute error. Absolute error is nothing but true value minus approximated numerically calculated value. This is the formula for absolute value. Take the absolute value of the positive value of the error, or you can take this. Okay, this is the absolute value. Absolute we know mod value. Okay, take the positive plus positive sign only. Relative error. These are the two important errors. The ratio of absolute error to the true value. What is the formula for relative error? Is nothing but absolute error divided by true value. The both value are already given in the example itself, or sometimes we have to calculate absolute error, then we can calculate relative error. And percentage error, next type, is nothing but just relative error multiplied by 100. Percentage, we know percent, multiply by 100 only to the relative error. Okay, let us see some examples depend on that.